This is a demonstration of the software setup and the bench setup for the ARNA robot by Duncan Ashworth in Austin, Texas with Floorbotics. So the first thing to show is the software setup from the Kill compiler produced by Silicon Labs. And so it's loading the ARNA test program that I've written. It's pulled up the currently it's on the motors. Here's the main.c. It's coming up. So here's the main.c routine. It uses the Kill compiler. So the way it's set up is there's the little dongle runs here from the PC to the ARNA setup here. So there are some key things to show on the bench setup for the ARNA robot. There's the display. Try to get a picture here. So that's when the test program first starts. It says press start button to begin testing. So that's on the LCD display. Then you can see here's the main circuit board here. In this case it's a FLI 409 PC board. Then there's the power board. Then there's the BLDC controllers located here. And then the BLDC motors themselves that are located here and here and labeled left and right. And then also have a bank of 1, 2, 3, 4, 5, 6, 7, 8, 9 IR distance measures, and each one is carefully labeled so I know which one is which type of sensor. So this emulates the IR sensors. This is also in the test program. Driving the motors is also in the test program. So the way the BLDC controller works is that there is an analog voltage produced by the main circuit board and sent to the BLDC controller, but the BLDC controller also outputs a chain of a pulse train, and then that goes into a counter, and the software looks at that counter to make sure that the motor is indeed turning. We found out that the BLDC controllers themselves can have different interpretations of the conversion of the analog voltage from the FLI board, and will cause the motors to run at different speeds, and those are all adjustable by a pot. However, I think the best thing to do is to always look at the pulse train coming back from the motor to regulate the voltage that the motherboard sends to the controller. So that's the best way, is to implement some feedback and don't just count on a certain DC voltage coming from the FLI board to give you a certain speed. You have to have that feedback in the loop as well. Here's the wireless connector. So this is connected to an RS-232 port on the FLI board, and this wireless communicator goes back to the PC for making for recording information. So that's so we'll do a little demonstration here. There's also the gyro board is connected here, so it's a little auxiliary gyro board. Let's see if I can get a better picture of that. So here's the analog devices gyro board. Here's the start-stop button. So you can see here I grab the start button, and then it says so that gyro, it goes through an auto calibration routine. In the defines file in the test program, I've not defined anything until it gets down to test 19, which is the gyro testing program. So it goes through, and since the gyro is not moving, it auto-calibrates itself and sends in a correction factor to the gyro off register until it gets an acceptably low number here. So then it's tweaking that offset number, and then what it starts doing is reading the gyro angle. So you can see it. So it's just gradually creeping up. It's almost 0.2 degrees, 0.1 degrees off, and so it just keeps reading the accumulated angle. So now it's 0.4 degrees off, and it creeps down a little bit. So there is a little bit of noise in it, but it's basically pretty good. And the worst case angle error that I get is about 2 degrees per minute. So that's about as good as can be expected. You can see right now it's almost 1 degree. But because it went off too soon, it goes back and recalibrates itself, and then it'll start taking long-term readings. So it's still basically in the main calibration routine, and then hopefully it'll catch a better number. Okay. Another thing that's used is the so I'm going to move this Silicon Labs IDE screen over here. So I also use Crystal Flow, which is a good documenter. So you put the same project build library in here, and get rid of this thing, get rid of this, and this. So this is Crystal Flow, and so you can put the same library in that you had before, and just load the program, and this is how you do your documentation. So it has all sorts of handy routines, such as flowchart builders. Okay, so we'll exit from that, and then the other thing is the QVT terminal. So we'll see this is the wireless data that's coming from the XB interface over here. So this is data spitting out of the RS-232 port. My development software and test software uses the printf instruction to talk to the RS-232 port, and then this is the receiver, the XB receiver, connected to a USB port over here, and this is the QVT terminal. It's a freeware emulation terminal. So here's the data spitting out, and then what you can do, if you want to capture all that data, you can also just go to this log file routine that's in here, and then name the file where you want to start saving all this data. So after this data is saved, any kind of debug information you want can be then post-processed and either use an Excel spreadsheet or a C routine, some kind of little script to process that and do anything you want to. But the reason it's a wireless connection from the mock-up to the PC is so that you can have a wireless capability and capture data from the robot itself as it's moving. But that's the setup here. Just lastly, I'll show you the batteries that are being used. So I've got 24 volts set up on these batteries. Okay, that's it.